Hello again, everybody. This is our third live stream of the day, preparing for version 15, and we're talking about mathematical computation now. So we've gone over a lot of this stuff already, right?
Yes, I mean,
Well, we looked over some of this preliminarily, right? We haven't had an actual design review of
Okay,
any of
let's
this.
see what there is here. Oh boy, Clifford algebra. I know what Clifford algebra is. I don't need a link to Clifford algebra. I need to.
the ref page, it's there. Yeah.
Right? It's a slightly generalized Clifford algebra because we also allow zero diagonals.
I wonder how the big red dog ended up being called Clifford.
What?
Clifford the Big Red Dog is a series of children's books.
Oh,
And
But
television program.
yes, but of course you do know that it's named after an actual Clifford. I forget his first name, but
What's named after an actual Clifford?
the Clifford algebra.
Of course, yes. Something like Kingdom Clifford or something. It has a very strange first name, I think.
Yes.
Oh, here it is. William Kingdon Clifford.
So these are dedicated. This is one of the new dedicated generators for non-commutative algebras that we've added, right?
Shouldn't we have quaternion? I'm very confused. We shouldn't really advertise this. We should be folding our quaternion functionality into the new non-commutative algebra functionality, should we not?
I think so. I agree. I mean, if there's no objection, let be a very good thing. I mean, it's very natural to do it because it's so much better with the the new stuff.
Let's do it. We don't have any need to stay compatible with a package. I mean,
no.
let's just
Well,
put
we're
quaternion
not
into the
trying
system.
to, right?
But
This is just, by
Okay,
way of
what would
example.
it? So, are we now in a position to put quaternion into the system, just like complex?
Adam can answer, but my guess is yes. Adam?
Yes, but not immediately with all the functionality of the package. It does more than just quaternion arithmetic. We could easily have quaternion arithmetic in system.
What else does it do?
Well, it computes several quaternion related quantities, which I don't remember what exactly they are, but there are several functions that it does.
All right, but we're now able to do a lot of fancy stuff, like essentially factoring over quaternions and so on, which we were not able to do before. Correct?
No.
No.
Well, what's all this Grosvenor basis reduction and so on?
We can do the Grosvenor basis and reduction, but not factoring.
Okay, so hold on a second. So,
I mean, and it's fine to sort of, to release sort of more broad support for quaternions. People ask for it, usually not for good reasons, but yes. And but one has to still draw the line, like, should we develop all the special functions for quaternions? Probably not.
No.
Right. But so we still have to draw the line somewhere.
Most of the special functions are barely defined for quaternions. Let's be realistic.
Right.
But right now, right, you can declare a Clifford algebra that represents the quaternion algebra, but right, you need to use that non-commutative algebra object, right, to have sort of a quaternion just completely freestanding. I mean, that would require some design thought about.
I know. I'm just suggesting that now is maybe the time where we finally can do that.
Yes, I think. I mean,
yeah, we could look at least at supporting the stuff that's in the quaternion package.
Yes.
Right.
I mean,
we should take a look at what use cases. Really,
right.
Go back to use cases.
I think the number one use case is rotation type stuff.
Right, but also our rotation transform addresses all the sort of interpolation issues involved that you kind of solve with quaternion rotations.
Mm-hmm.
So there are other alternatives, but having said that, people are used to it and they expect it probably to be there. But
yes. Yeah. But I mean, it might just convert into a quaternion transform. So that might be the path. But then there are more symbolic things where we're going to have to use the Clifford algebra in algebraic form, I would think. All right, so where do I get gamma matrices?
Well, you can't currently get actual gamma matrices.
Yeah, so these are abstract algebras. They are not matrices. They don't have any structure other than being an algebra.
Right. So in Clifford algebra, I have a couple of examples about the Dirac algebra. One of them can probably be simplified a little bit with new functionality.
Right.
So, right. So there's the Dirac algebra, right? And right, these are sort of abstract gammas. And right, then if you write out the, Dirac's matrices, then you see that they're a representation of this abstract algebra. And you can learn all sorts of nice things about, the Dirac algebra from the purely abstract point of view.
I didn't know this relation. I probably should have known that relation, but I didn't know that relation. Actually, maybe I did know that relation, just not in quite that form. But okay, but so explain to me, like in the case of a group, for example, there is the generic group with its relations that are generically true of a group.
Yep.
And then there is the much fancier, and I'm dealing with this particular group that has the following known, relations between its generators. Is that the same kind of thing we're dealing with here?
No. Well, yes
Well,
and no. Right?
you can do any algebra given by generators and relations. That's basically what it is.
Right. So right, but the different right. So what you have is yes, I have an algebra with these generators and these relations between them, right? Like that these square to 1 or minus 1.
Yes.
And you can do anything you can do with those sort of abstract elements. Now, if you want actual Dirac matrices, then right, that's a algebra representation.
Yep.
Which which is something we don't have, and we don't also have a generator. Danny worked on something, but then I looked at what he was doing and I realized the code that he had been given only did the Euclidean gamma matrices, which I didn't think was useful to have only the Euclidean case. And
well, I mean, there are a bunch of conventions about how you deal with, you're talking about Minkowski versus Euclidean.
Yeah, exactly.
And in particular, you've done the Wick rotation, so you have actual Euclidean, not x4 equals ICT, which is a fine thing to support, but that shouldn't be the default.
I agree.
Right?
There's a spelling mistake here right in front of me in that highlighted thing, Kronecker.
Oh, there is Kronecker. That should be Kronecker product.
Okay. I do that a lot. Sorry. I'll spell check it before it chips.
Look, just so I understand, with generators and relations, I could perfectly specify like the icosahedral group or something with its generators and relations, right?
Yes.
Yep.
Yes. Is that actually there is an example somewhere on the commutative algebra page that does a group representation.
Okay. So is it efficient? I mean, dealing with, if I want to know, I see. So that's a with the generators and relations, I get that. I should be able to get a Cayley graph from that, right? I don't need any representation. I just need the generators and relations, do I not?
I believe so, because I would be able to answer that better than I can. But I think
of that. So the question is, given a bunch of generators and relations, could we generate a Cayley graph or other such objects? From an algebra, can we generate a Cayley graph of some kind? I guess we have to know that it's a finite. I mean, if we want a finite Cayley graph, we have to know that that set of generators and relations represents a finite object.
Right.
A finite algebra of some kind.
Right.
Is
right.
that
So
yeah, go ahead.
if you look at the example there, we can. So there is an application example where we actually proved
And which
on non-commutative algebra page. The non-commutative algebra new, sorry.
I'm sorry, what is it called?
Non-commutative algebra new.
New with a new appended.
Where is it?
Applications.
God, it'd be nice when we have this thing that allows you to see which I thought that was coming in 15. The thing that allows you to see which cell you're over. Okay, in any case.
It's further down.
Okay.
Oh yeah, so this basically
Do send in dicyclic as a spelling word. Is that what it's usually called? I thought it's called something. Isn't it? Isn't it usually C something or other?
That's how Wikipedia does it.
Okay, I don't know. It seems wrong to me, but whatever. Some random person added it to Wikipedia and thought they were being very clever. Okay. I don't understand. I think this isn't. Oh, I see. It's a cyclic group of order 6, and then it has this extra relation x squared equals a cubed. Okay, so this is the representation in terms of monomials.
Right. So and we can prove that there is exactly 12 different elements in the group.
How?
So that's the whole thing. We compute Grobner basis of the relations, reduce everything that's of order 5, and it reduces to things of order at most 4, meaning that there is no reduced polynomial of order more than 4, and we can just enumerate all of them, those of the order 4, and we get 12 different reduced forms.
Okay. Okay, let me make a generalized comment. I am basically certain that there's a bunch of additional packaging of all of this functionality that will make it vastly more useful to people.
Right.
Yeah,
if we want something specifically for groups, then we probably should package the whole thing that I written here.
Yeah, I mean, whether it's for groups, whether it's for gamma matrices, whether it's for quaternions, all these things are known brands in effect.
Right. So we did one extension from last time, the Clifford Grassmann while this time. Question, should we do more? And I already have one from the while algebra, is not the one we're looking at now, but the while algebra is for differential equations basically. And what Adam has done is to very nicely crack the problem of solving systems of overdetermined PDs like killing fields and killing vector fields and all that. That's an example. That's an application example.
I think it's below this one. Yeah, if you go further down, it will be there. No, not this one. I guess I put it in on the while algebra page. Yeah.
Yeah, on the while algebra page, so he's actually done. It's pretty deep and immediately usable for desolve. It's like just a bit of work and then we are done, I think.
Okay, but that's a use case, which is wonderful. I mean, that's how we get real power in the system, is being able to, we think we're solving a differential equation, but actually we're using some complicated Grobner basis of Weil algebras.
Yeah.
But the point I'm making is, I know about quaternions. I've heard of quaternions. Somebody's explained quaternions to me. The fact that I can think about them as some Clifford algebra is a much more advanced concept.
Oh, yes.
Right? So I'm saying we should support, but basically it is not a high cognitive load to introduce quaternions, gamma matrices, everything you've ever heard of that is, a Grassmann algebra. I don't know whether these supersymmetry things count as being popular enough, but all these things which have branded names, we should just introduce them. We shouldn't
Right.
say, to do a quaternion.
Right. So these Grassmann algebras is just the exterior algebra. The super algebras have an additional structure that we can't represent.
Okay.
And certainly we wanted to have a Dirac algebra, but then when we discovered that Dirac matrix itself wasn't ready, then we decided to hold off on that until Dirac matrix is ready, which if I suddenly get a lot of time in the next month, maybe I can make it happen for 15, but more likely will be for 15.1.
15.1. So Matt's Berami has cracked the problem for gamma
I mean,
matrix.
I think it's a little bit like finite fields or something. I think we can introduce these things at a certain rate, this better packaging that you described, Stephen.
Yes.
Because I think that there's like, it's a bunch of utility things around it to get the workflows right.
No, I agree. I'm just saying that we're not finished here. We gotta polish the thing.
Right. And while algebra, we're using it implicitly deep down, even for ordinary differential equations by factoring differential operators and other things. But that's not visible, But so like for Weil algebra, we probably need to introduce operator syntax, differential operator syntax and other. So there's a bunch of things that comes along that has to go in addition to make that.
Yep. I mean, we're gradually recapitulating the history of mathematics.
Right. Yes.
We've which is a fine thing. All right, let's look at some of these. Atomic output to support non-commutative algebra with relations. What's that?
This again the new page. Yeah, I think you just closed
the new.
The one just closed probably.
Oh shoot.
Right. So the atomic is just about the internal implementation. It's
okay, but what are you telling me here? It's one of these things that's one of these specifications?
Yeah, so we added more than half of them in the new version. So everything. So generated relations, commutative relations, structure, and variable order and word order is also something that we added. So we can now have.
I get it.
Right. And so what's Weil algebra? It's just a constructor that sets up a non-commutative algebra with the correct option set. So so it's really just packaging.
What is the relationship between like find equational proof and its generators and relations and non-commutative algebra and its Grosvenor basis reduction? They must be very similar at some level.
Yeah. I mean, it's a Knuth-Bendix completion in both cases, like they're S polynomials and that whole thing.
But I wonder whether one is vastly more efficient than the other. My guess is this would be much more efficient than find equational proof, and maybe we can use this for that.
Not sure. I mean, one of the things is that in general, this one is infinite. So I'm saying
what do you mean?
So in general, the non-commutative Grosvenor basis is not necessarily finite for these non-commutative algebras.
Yes. But
I don't know, but how about find equation? Are those always?
So those are infinite, right? They may fail at some point. It has, I think, some bounds or how long it will go.
I see.
Look, but
so
basically what it is, Roger,
same story.
I mean, it's a bunch of generators and relations, and what you're trying to do is prove that one word is equal to another.
Yeah. Same thing here.
Right.
Yeah, I think the algorithm itself is somewhat different or can be more efficiently implemented depending on what you are trying to do.
Right,
So,
but the question that I have is, I mean, like, for example, could I write, my little favorite axiom system that I found for Boolean algebra? I could presumably write it using non-commutative algebra, could I not?
Yes
Am I
and
wrong?
no.
Yes, probably, but
right.
Why couldn't I write this as a relation in non-commutative algebra?
Yes, and then prove things by reducing with respect to the Grosvenor basis of this. Yeah.
Right. So what I would expect to be able to do, let's say with this, okay, let me show you an example. I mean, if I say find equational proof of P dot Q equals Q dot P with respect to this, right? Then it'll grind for a while and it'll give me a proof. Okay, but it has a proof object, which is a different kind of thing. Now let me try and do the same result. What would happen if I tried to do the same thing with non-commutative algebra? Tell me how I do it.
You take you make a difference out of the
Okay, non-commutative algebra, and then what?
no, you need to do non-commutative Grobner basis of the
Well, I mean,
of this equation that you have for the axiom. So
Okay.
so you take this, change it to minus.
Which maybe shouldn't be necessary, but yeah, okay, let me go ahead. Yes.
Then try, well, you have to come up with variable order. So I would say double bracket ABC. We are not sure what, so.
Double bracket, what do you mean, double bracket?
A double brace.
Double
You mean
brace.
list.
Yeah, something like this. And
I'm just gonna,
actually the double and the list inside, yeah.
I'm just using this to
And
get those.
then you have to do non-commutative algebra with multiplication going to whatever is the name for this dot.
Probably
Okay.
center dot.
Yeah. So what do I do? Non-commutative algebra.
And then the option is
By the way,
the string.
you should probably make it so that it auto-completes in this position correctly. What do I do? Multiplication.
Multiplication goes to center dot.
Yeah, the symbol center dot.
Do I run it?
Oh, looks like it's
Yeah.
okay.
Go.
No,
What the hell did it do? What are those squares?
these are squares with
Oh, I see
respect
the
to
squares
the
with a
dot.
Yeah. Okay. All right. This is cool.
Now
Now what do I do?
try reducing. Well,
P
how
dot
do you?
Q dot P minus P dot Q. Why not?
Oh, but that's not done. No.
Right. Yeah, but see, right, we get into the quantifier, right? Find equational proof
How
has some sort of trick, which maybe Jose can explain, to convert the quantifiers into equational statements, right? Because ordinary equational logic does not have there exists and for all.
Right, so you
Right,
can
but this
do it.
assumes.
You
Yeah, go
can
ahead.
actually just use A dot and B dot. So the same thing. So if you prove that two of them are, yeah, I think that's pretty much equivalent to, since there's nothing special about them. So or is there?
I
Yeah,
think that it will not be valid to do this.
there is I think there is some more
Okay,
logic
so
we
tell me what I do.
develop there. How do we go from
Okay, tell me how I would do
this
this with this particular thing, which probably will be easy to do. So how would I reduce this with that Grobner basis?
non-commutative polynomial reduction, actually? So the new function, you just want the remainder.
Okay, of this with respect to that basis, correct?
Yep.
With respect to the basis, and you have to repeat the variables and the algebra.
The A, B, and C.
The A, B, and C, yeah. So
you can copy.
Just copy the rest two arguments. Okay, and that didn't work. I guess we didn't get the logic right. So for going from for all to some specific things.
Yeah, I think.
Well, it would be interesting to see what the correspondence is here. I mean, this is a somewhat non-trivial proof here. I would be kind of amazed if it degenerated into something simple by this methodology, but it would be very interesting if it did. I'd like to see this.
Yeah.
Yeah,
I think we need
to
have
think about it to get the
yeah.
correct translation of what it should be. Yeah.
Okay. looked at these examples. You should have pushed me to look at these examples.
Well, I put them just a few there just for you to have a quick view of what's there and what you want to do with. So this is just a nice speed up for requested on Stack Exchange, I think, yeah. And of course, you know about this one.
We've talked about this.
Yeah, and I think this is kind of a good place to have an alternative to
I
apart.
don't like this. I'm sorry, I don't like this. You know, this is again a slippery slope of changing. I mean, that would be, you know, integer part, fractional part, right?
No, but we do. I mean, so the question is, when you do one of these things, do you do it to admire it, or do you do it for a program?
I know, but if you do it for a program, maybe what we should do is have functions, you know, polynomial part and, you know, fractional partial fraction or something. Just bite the bullet and say it's just like integer part and fractional part, but for polynomials. See what I'm saying? I mean,
well, I don't know how many possible strings are possible here, but
how many
I mean, polynomial part sounds kind of mysterious to me. Whereas in the context of partial fractions, then that makes.
Yes, I agree, but maybe there's a name for the you know, the ordinary polynomial as compared to the fractional polynomial. I mean, that's a naming question, but it seems to me better to make it analogous to fractional part. I mean, we're not calling it, you know, integer decomposition, you know, comma, quotes, fractional, integer decomposition, quotes, integer. See what I'm saying?
I want to look over what all those things are there, because I think that there are more, you know, having written this function myself many times and used it many times, there are more accessors that we need, you know, to efficiently use this in code.
Right. If you look at the rough page, there are, I think, 5 different possible second arguments listed.
Yes.
Yeah. But I don't think,
I mean,
some of them are more useful than others. I suspect that, you know, it's like.
But for instance, you know, but you need to know, for instance, like first order parts are usually very different from second order parts, even in the rational part. Like if that was saying 3 over 2 plus x squared there,
yeah, right.
It's very different from 3 over 2 plus x in terms of how you.
It's differently poly, but in complex analysis, for example.
Right. So if you integrate, for instance, one gives a logarithm and the other one doesn't. It's very different.
Right. I'm agreeing that I think we should try and name the accessors.
Yeah. But I think that if we start, I think we should have accessors, but I do think that we should think more about workflows, because like actual application use cases.
Yeah. But I mean, I'm suggesting that you're right, that we should name the functions, not have it be sort of a backhanded way where we say partial fractions, a polynomial part plus 7 partial fractions of fractional part.
Oh, you want other functions?
I want other functions.
Which obviously.
I mean, how many? Like 5 more functions?
Yeah, I think this is well. I mean, honestly, if it didn't have this, no one would complain seriously. It's just something we wanted to do. And I feel.
But I think it's very important, because the other thing does not address programmatic use.
Yes.
Which other thing? You mean this thing here?
This thing does address programmatic use. It just needs to be extended. You know, the thing that just returns it in a typeset.
No, I know it's not particularly useful. I agree completely. I'm saying just like you can, you know, quotient and remainder are useful functions.
Right.
Or numerator and denominator are useful functions. Even though you could say, you know, even though you've got the fraction sitting right there on the screen, you could say part 1, part 2, etc., etc., etc.
Well,
the other thing is that it's just also very inefficient to have many functions where you call separately repeatedly. It's like it's the same work you do. It's just, you know, you want to access different parts of the result.
I understand. So, this requires more thought, in my opinion.
Yeah, so I think we should bake this one just a little bit more and come back in a follow-up.
Can I make a suggestion? Maybe what we need is partial fractions and then partial fraction list.
That's what I was suggesting.
That's what we thought early on. We thought.
But I think that we should do, like, the modern way of doing that is not the 35 years ago way to do it was that. But now we have associations and other things. I think we can
that's a
do
good
better.
point. It's a good point.
Yeah.
Okay. All right. And maybe this thing here, maybe it becomes, in our partial fraction rules, and that becomes an association, and that's equivalent to these accessors here.
Yeah, we can do something like that. But that's basically what I wanted to do, because I think we want to make it easy and efficient to use in programs, not
Sure.
only to sort of admire. That's
No,
useful
no.
too. It's not, don't get me wrong, that's also useful.
All right. So this particular form is ready.
Yes.
The other forms are not really quite ready.
So what we want is partial fraction rules, which will bake in the full association for all the different things that Roger and might want. I mean, we have 4,
Yeah,
5.
that's what I'm suggesting. Yes.
Yeah. So just 2 functions then. Partial
Yeah,
fraction.
but I'm not sure
Yeah.
this is quite right. You guys should think about it some more.
Sure,
Yeah.
sure.
My God, new matrix decompositions.
Yes. So these are kind of standard thing in the field. So this is like a generalization of Cholesky. And the LDL has been, it's there like in every other system, including APAC. So the docs need a bit of work, but basically.
Okay. All right, fine. Well, but I mean, the form we're giving as output from these decompositions has always been a bit of a mess.
But that's what since we have structured matrices, it's no longer going to be a mess.
But this is giving an ordinary matrix, not a structured thing.
Right, which is not as useful because you can't really use
I mean,
it.
we're introducing LDL decomposition, and it's giving. I mean, are we going to have a decorator on these names?
No, so there's I don't know, but I don't really like that to be the default, to introduce the unstructured form, because they're unusable except for admiring them in the following workflows.
Yes, I agree. But I mean, maybe what we want is something like
So
LDL
why,
decomposition structure or something.
so why does the next one give structured ones? Is it because of the size? So
I don't know.
Okay.
This doesn't seem right to me. So what we did for compatibility reason is to introduce an option that says target structure, but the defaults are set all wrong.
That's horrible. It's really horrible. By the way, why is it called a Pfaffian det as opposed to a Pfaffian?
Well, I think that I know it's called Pfaffin, but Roger, you felt that it should be more in the spirit of what we do ourselves. I mean,
well, what I would call the Pfaffian is the matrix of second derivatives.
I see. Yes, that's what I would call it. What the hell is this?
This is actually a determinant.
It's the square root of the determinant of a skew symmetric matrix.
Yes.
Well, then it isn't a Pfaffian in the ordinary sense.
Yes, so that's what we call Pfaffin det, and this actually was requested at some point, and it's not high priority, but it's something that, and it's quite efficiently done. So there's lots of methods and.
Well, I don't know the naming of this. I mean, Pfaffian. What's the relationship other than Mr. Pfaff invented them both, or didn't invent them, as the case may be, between the matrix of derivatives and this thing with matrices, the square root of the determinant? What's the relationship between those two constructs?
Is there a relation? I don't know. I mean,
well, is it just that it happens to be the same dude?
I think so. But,
probably there are also Pfaffian functions that have nothing to do with either of those.
Okay.
Interestingly, on the Wikipedia, if you search for Pfaffian, the thing that comes up is the determinant one, not the derivative one, which I find slightly surprising.
That is
I think it might be the same confusion between Jacobian and Jacobian determinant. Like some people, when they say Jacobian, they mean like the determinant because they're doing integrals or something.
What? I mean,
well,
that doesn't have anything to do with derivative. It's just determinant.
Right. Well, except this Pfaffian has nothing to do with derivatives, unlike Jacobian and Jacobian determinant, which are both derivatives, both derived from the derivative, right?
Yes.
Yes.
Johann Friedrich Pfaff. is the determinant one.
It has to be the same FAF who did the other
Oh, it's the
one.
same FAF. Oh, yes, I think so. Yeah.
Yeah.
Another one you're referring to. So just
Okay.
if you're looking at the matrix function, that's from something that you had requested, where we had these dramatic improvements, the speed improvements from WFR. And I don't know there's much on the page itself. I mean, the only thing that changed is the speed of those examples,
Okay.
but they're dramatically faster. Like
I forgot what was done. It was some algorithm change.
Yes, yes. So it was done. I mean, Danny had a note about it in a bigger notebook, but it was requested by you at some point. Yeah.
There's quite a bit else to do here. We're going to have to meet another time.
Are you trying to stick to a schedule?
I am trying to stick to a schedule. I've got some stuff that is supposed to go out today, so
I see. That's fine. Wherever you want to stop, we'll schedule from there.
Right, and we haven't talked about the change to LU decomposition.
Oh no, what is there?
Oh, that's been a long battle, and I think we finally have a solution. Oh, you should look at again new. I'm sorry. Please look at the LU decomposition new page because that's completely redone with the new design.
But is it compatible?
No.
No.
That's why we need to talk with you. So so you said you want structured output. Well, we give it, but then you break the.
But you can make it compatible by setting an option. If you set the option, you can make it compatible.
Yeah.
I mean, this is the right.
If you
You've
type
complained.
normal, does it do the right thing then? Does it go back to the other form?
No, because the other one is trying to pack those two matrices into one. So normal cannot do that. The lower and upper triangular get packed into one in the old.
I know, it's a horrible thing.
But the thing is that you can set the option. If you want the target structure to be classic, you can get it.
What's that 0 at the end there?
Condition number.
And for exact, there is, the.
Yeah, okay.
That's
Why isn't this an association? Why isn't this result an association?
We never do that for the matrix algebra.
I know,
Yeah,
we haven't done that. Look, I don't think that breaking compatibility is a great idea for something like this. And I think a better approach would be.
I mean, no, not a stupid name. Why would we? Is that what you're going to propose? A new stupid name?
An alternative name. Yes, I'm going to propose an alternative name.
I don't think it's a good idea. I think this is what it should be. Like,
what would happen if you said LU decompose?
Okay.
Why would you break it for this?
Because you're going to have code that people have written.
But you can set the option, and it's.
But they won't do it. They won't do it. The code will just break, and that's not something we find acceptable.
We have plenty of places.
Yes, but not very many.
Okay.
Very rare.
Yeah, halfway house that. Why don't we switch the? I mean, if Roger agrees, then we switch the default to still be the one that's current, and then target structure goes to structure will give the new one.
Okay, so all Stephen's complaint is to maintain some kind of compatibility.
Yep.
And then it's stupid. And then we're going to have that discussion again.
No, we shouldn't do that. What we should do, here's what we should do, Roger. We should figure out a new name that makes sense. We should advertise a new name. We should deprecate the old name. But people who are still, who have code from 35 years ago that uses the old name.
But then we rename everything so they all have this new consistent name.
That's correct. Yes, all the matrix decompositions. I think that's the right thing to do.
Why do you insist on that?
Because I want to maintain compatibility, because it's a really important thing.
This is the only one where we've actually broken, by the way. In no other place have we done it for any existing decomposition. So.
Well, why not? I mean,
because I think it's not worth. Honestly, the people who work with these they are pretty advanced users. I think they really want.
We should not break compatibility. Period. No, end of story. So
I totally agree.
With a different...
So for just this one, we have broken it, and
let's not do that.
Okay, fine.
It's even worse that we're doing it for just one.
Yeah, exactly.
I don't know what the right way to do this is in terms of the naming and so on, but I don't understand why we haven't broken it for other ones, because aren't there other places where you've packed matrices together?
No, never. There's only one.
By the way, I want you guys to know, even though I think none of you were around at the time, I complained when this was originally designed this way. I said this seems stupid. And I was told, oh, you just don't want a thing that's a ragged matrix. You always have to have a, an actual matrix.
Yeah, but they
Even if
didn't.
it's
They didn't have structured matrices at the time because
Yeah.
you need more. Okay, so if you do this like in LAPACK or something like that, you, the user, need to be aware of that this is going to return something, and now you, the user, need to know that you need to call a different linear
I
solve
know.
function.
Yeah.
So you are responsible for code administration, basically. You're going to use a forward substitution or a backward substitution solver, which is a
Right.
particularly
But so,
simple.
Roger, let me make a suggestion.
Mhm.
Given that workflow, maybe we should think through what the right thing for an LU function to do
But that's
is.
what we've done, Stephen. I've tried to explain it to you. If you give those matrices to linear solve, it will do the right thing.
But not in a list like this.
Of course it will.
No, not in a list like this. If you give that to linear solve in that
No,
list,
but that's not the use case. I mean, that is the
I-
use case for linear solve, but you can use LUs for other things.
okay, but let's understand what those are, because I don't think
But
that
we list
this,
up there, we explain what the other pages never explain the use case.
no, I understand, but Roger, here's what I'm suggesting, okay?
Mhm.
I don't think this form where you say LUPC equals whatever is a great form. I think
Okay.
that whatever is the later workflow, rather than picking out element 2 in here or something.
But there isn't only one. That's the
I
that's
got
the
it. I understand there isn't only one workflow. Okay.
Okay.
I'm suggesting that I don't know what the right form is. I don't know whether it's an object that then gets poked at in different ways by different functions. What it is, I don't really understand that. But that's what I'm suggesting, is that we figure out, because this is not very convenient. It's like all the return forms, whether it's, I don't know, find shortest tour, where you have to pick out element number 2 and things. That's
Mhm.
always been very inconvenient. And now we're just, given that we're revising
no,
this, let's
no,
figure that out.
I disagree. I mean, if you have like 17 elements, sure. But for most of the decompositions, you get back exactly 2 things, and being able to just say, ST equals blah is incredibly useful. If it's an association, you can't do that.
Okay, but let's think that through more carefully. Let's look at some code that makes use of this. Let's understand how this is wrapped in other code. Okay? I mean, if
this is the
gave an
applications of
association,
them. So decompositions is kind of like polynomial code. It's like a what do you call it? A sort of a half. It's like a building block. Okay.
yes.
Okay, but it's a very horizontal building block. It can be used to for a variety of use cases.
I get it.
Okay.
Okay. I don't know what the right solution is here. Okay. One solution that isn't the right solution, okay, would be something like, that LU decomposition returns. This is not the right solution, but I'm just going to make this point as a, that's the lower matrix, et cetera, et cetera, et cetera. So that then what it looks like is you say decomposition equals this, and then you say decomposition L is blah. For example, I'm not sure that, I don't think it's right. I don't think it's completely bonkers, given that it's
But that
called
means
LU
it's
decomposition.
everything is a multi-step process now.
No, but everything is a multi-step process because you have to extract the elements from this.
But you already did LUPC, extract the elements.
I know, but I don't think that's a good
There's the L value.
metaphor. I understand. And then you're using them in different places.
Right.
Maybe that's the right thing. I don't know. I'm skeptical
Mhm.
that they are so independent of each other, so to speak.
No, they're not really. You
Okay,
can
so
see the
fine. So
relationship that holds there.
Let's look at what code you write around this. Okay, let's look at the different forms of code you write that make use of LUPC in different ways.
Well, suppose this were eigenvalue decomposition, right? And you're doing a quantum problem.
Yes.
Right. Well, of course, you're going to exponentiate the diagonal matrix. And you'll only use the 2 unitary matrices, at the very edges of whatever formula in order to transform in and out of the
So
diagonal
in that
basis.
case, what you're describing, it reminds me a lot of root sum or something like this, where you're basically saying, I've got a function that I'm going to apply to these different elements of, that come out of the decomposition. See what I'm saying?
Yeah.
And the real thing you're doing is taking those elements of the decomposition, rather than having them as separately hanging out Fortran variables, you're basically taking a symbolic function. I mean, this is an inside out, outside in story again.
No. So we
No.
have a function that does that for you. You never need to do the eigen decomposition. You have something called matrix X. It does it. Or matrix power. It already
Fair
does
enough.
it.
I understand in that case. I'm just saying in this case, maybe what one needs is something which takes a function and applies itself to these elements, the lower, the upper, etc. I don't know if that's right.
No.
Well, why do you say that? Look, let's just see some examples, please, of code that uses
Look
this.
at what the examples are. The application. Look at the applications. I mean, I don't know how well filled in this is, but
yeah, I got to run off right now.
Well, I can try to make a pass through the applications for next time, so that assuming next time isn't tomorrow, then I can try to make a pass through these and have some more a better filled out application section.
Yeah, because these mostly seem like
I feel strongly that we have the best packaging of anybody. We have the structured matrices. You need to be mildly aware.
Great. So that's fine. Let's not break compatibility.
And I think we should return them by default. I think we should get rid of this.
I agree with you, Roger. I agree that whatever function it is that we most advertise for doing LU stuff should return these structured matrices by default.
All of the decomposition, because that's the whole purpose in life.
I agree. So let's figure out how to do that in a compatible way. I don't know what that is yet.
Okay. I know you need to go, but yeah, okay, fine. We can talk later, but I think something like that. Yeah.
Okay.
Sure.
See you later, guys.
All right. See you.
Bye for now.
Bye.